Hey everybody, so I thought this would be a unique and fun video. It was a unique and fun project for me to work through. So to me, science overall is all related, right? There's no individual branches of science. Like I think that physics is related to chemistry, which is related to earth sciences, which is all related overall. And I think that's you need to have that mindset when it comes to AI and understanding and working with AI, because it's all, to me, complex systems is what it all boils down to, right? Is we're dealing with complex systems and complex systems working together. Like I saw a very fascinating video the other day where they were zooming into a microchip into like a computer, a CPU, and then it was like 60 frames magnification and then 120 x magnification and then 240, etc. And then it was like different layers, like going through a city, like almost just and then it was each of these layers. If you're looking at the magnification before, you wouldn't know that they even exist and that they're even there. And then it's so with that concept in mind, I've been experimenting and thinking a lot more with regards towards science in general. And then I work through a lot of these things with like LLM models and AI models, right? Like a lot of people ask the question, like, so like, what's the usefulness of these models? Like, what can you actually get out of them? And then to me, it's things like this, right? And being able to explore avenues and create things like this. I never would have created this without AI overall, like flat out, right? Because I never would have been able to go through every single element of this that I needed to work through to get to this point. And then so to me, that's where AI steps in, is if you're willing to ask the questions and you're willing to be creative and you're willing to take those steps and explore and then go down those paths, you have an avenue to fulfill to get something at the end of the road, right? Like this could have been in the past, like a philosophical pondering that ended nowhere, as opposed to now we're looking at what will be a GitHub repository. We're looking at full-on code, video, etc. Right? So with that being said, let's break down and look into exactly what this is. So it's an element simulator, and then up front, I went through and I tested like the interactions and what its predictions are, and its predictions, like I spot tested like maybe 10 of them, and they line up, but I'm not a chemist overall, right? And chemistry is not my main area of science. What I want to point out within this though and highlight is that like a lot of people, you might think like chemistry is like beakers in a lab and all of that, but chemistry is exactly what we're looking at here, right? A computer science at this point. And then so just diving into this, starting off, I have created two classes. Class 1 is element and class 2 of interaction. And then so very straightforward, right? Elements are the different elements of the periodic table, and then the interactions are the ways that those elements can interact based off of two criteria that are listed out in the elements, which are their electronegativity as well as the valence of the electrons. So electronegativity and valence. And then also they're delineated and defined by their symbol as well as their atomic number on the periodic table. And then so when you go down and you look at the elements here, I have some of them defined. I don't have every single element on the periodic table defined here, but you can see I have a lot. I have I have 1 through 30 flat out, and then 35, 36, 47, 53, 54, 79, 80, and 82. Just went with the common ones, right? So like the upper ones are, you know, like gold, mercury, lead, silver, etc. Right? And then so going back up here, so everything else is, so these are the classes that I've defined, and then we have functions, right? And then so these functions are interacting with these two classes, element and interaction, and they're doing different things with them. So very first function is simulating the interaction process and exactly what's going to go on here. And then it's, in this instance, it's, I'm a big fan of this, Monte Carlo simulation in Gaussian probability space. And then so in this instance, it's simulating the ionic and the covalent bonds between them. And then so I just provide the math there, and then it simulates the bonds. And then it looks for and defines stable reactions. In this instance, like every reaction that it printed out is like above like 98% stability, like I think 97% or so. But you can see here, I put the cutoff at 60%, and it doesn't get anywhere near there. and then the rest is just to visualize. And then we have a visualization, and the visualization to me is really cool, and I'll get to that in a second. But so we go down, and then we can see here, here's our reactions, right? And then so here's what it prints out. 92% looks like it gets down to on some of them. But so for helium, for hydrogen and helium, HHE, and I didn't know, like, I didn't know that that could be a stable bond apparently. But so going through all of these, you can see that it's like it essentially how I wrote it is that it takes each one of these elements. So hydrogen, for example, is like then gone through at some point with all of these different elements, right? So hydrogen and helium, hydrogen and lithium, hydrogen and carbon, hydrogen and nitrogen, hydrogen, oxygen, etc., right? And it tests the combinations, and then it's essentially looking for like anything that's stable, and then that's hugely stable, and then it will print out those stable interactions, and then we can see that there's a lot of them, and then just random ones here. So Si silver, and then so a lot of interactions like with like silver, and then some of these I spot checked. I spot checked them just to make sure, right? Like I checked one of them. It's a theoretical alloy actually between it's a aluminum silver alloy, and then so that's the interesting thing within this too, right? Is that some of these are theoretical. So like kind of the next step that I would do within this to like clean this up is like, and it would take a lot more work within the code, right? Is because I have to define it, know it, and keep it updated. Like which ones of these are like theoretical, and like which ones are like have actually been proven out, and like which ones like are stable at like room temperature or things like that, right? Because that affects different things. Like you can have several different classifications of stability. Like it could be stable at 0 degrees Celsius, or like or 0 degrees Kelvin, and like like that's a big difference than like having it stable at like 70 degrees Fahrenheit, for example. And then so going through. And this is the big thing. Like this is like to me like the gold that comes out of this. Like I don't like to me this is cool, really super duper cool to look at, which is the visualization that comes out of all of this, right? And then so this is all of the elements, and then so the hydrogen, helium, nitrogen, etc. Iron, and then going through lithium, you can see just all of the different elements that are listed here, and then all of the different interactions between them, right? And then so to me, like we look at often the periodic table as like a table, as a 2D element, but to me that misses the core, like it misses a gap. There's something missing within that framing of this, and that's like kind of why I set out to explore this and why I set this up. And this is my initial explorations within that, right, of that realm, that the way that we represent elements within the status quo, this kind of 2D representation of like here's the elements and then here is their atomic structure in and of itself, doesn't really do anything or mean anything. To me, it's more 100 times more valid and important. Like here are these elements, here's the atomic structure, and then here's the atomic structure of this other element. And then when you combine these two elements, their atomic structure gets you this web that we're looking at, right? This 3D sphere of relationships that occur, and like a massive, like it's like really hard overloading the visualization of the Python that we're looking at here, right? Like with all of the interactions, and it's like 30 elements, 35 elements that we're looking at here. So really cool overall, right? And then so I'll leave a link to this particular collab notebook in the description of this video. And if you like this type of content, please like and subscribe. Thank you very much.